We are going to take a look at graphing quantitative variables in section 1.2. And so by the end of tomorrow's set of notes, we'll be able to make dot plots, stem plots, and histograms. And then we'll be able to describe the shape of a distribution and then actually completely describe a distribution using a set of features. And then we will also use those features to compare distributions. And then finally, tomorrow, we'll take a look at some things with histograms that could potentially be misleading. So we want to make sure that we're using them wisely. So dot plots are one type of quantitative graph that we can create fairly quickly. And it's something that when we get back into the classroom, we'll be doing fairly often just because it's a graph that you can collaborate on very quickly. You did see a dot plot with the miles per gallon in kind of the introductory set of notes last week. And a dot plot really just shows a number line with the values plotted as dots above their corresponding values. So in order to make a dot plot, you're going to start with a labeled axis. So you'll draw a horizontal line and label it with whatever you're measuring. And labeling is very important in AP statistics. So we just want to make sure that everything always has a label and a title. And then you're going to go ahead and scale that axis. So you'll look at the range of your data set and then use that range to determine what a good start and end point is for that horizontal axis. So it does not have to start at 0. We can start at the minimum value for the data set. And then you go ahead and plot the points. So you'll put a point over each value from the data set. You do want to be careful and make sure that you vertically stack those points evenly, because similar to bar graphs, your eyes are kind of responding to that first glance. And so if you spread all of those points out in one section and then really crunch them together in another, you're not going to get a good overall idea as to what that distribution looks like. So here's an example real quick. We've got the number of goals scored by the U.S. women's soccer team in 2004, and we want to look at the overall range of values. So the lowest number of goals is 0 here, and then the largest is 8, it looks like. So we want to make sure that our number line ranges from 0 to 8, and then we just plot each of those values above its corresponding point. So this value here of 3 comes over and becomes a point over here at 3, and then the 0, a point at 0, and so on. And then again, we do label everything. So in that case, with the quantity of number of goals scored. We also can examine the distribution of a quantitative variable. So we're going to go ahead and describe the distributions, and we describe dot plots, stem plots, and histograms all in the same way. And there are kind of a very strict set of descriptors that we go ahead and look at. So here, we want to make sure that we're looking at that overall pattern and then any deviations from that pattern. So in order to do that, we're going to describe that pattern using the shape, which we'll talk about in just a minute, the center of that distribution. And for right now, we're just going to talk about the center being kind of the median or the mean. And we'll talk more specifically about both of those terms in section 1.3, but really the median just being the middle value and then the mean being the average. And then as far as the spread goes, for right now, we're just going to talk about the overall range. But then in section 1.3, we'll have more descriptive measures of spread that we'll take a look at as well. And then those deviations or departures from that pattern are what we call potential outliers. And so anything that just doesn't seem to fit the general trend, for right now, we're going to identify as a potential outlier. And then we'll have a rule for checking outliers in section 1.3 as well. So your book uses this acronym here in terms of what you need to address when you're describing a distribution. They say don't forget your SOCs. So S for shape, O for outliers, C for center, and S for spread. When you are describing a distribution of a quantitative variable, you're going to go ahead and do that in a few sentences. So just like a short paragraph. As far as homework goes, if you want to just do a quick bulleted list of the SOCs, that's acceptable. But for tests and quizzes, AP exam in particular, you do want to make sure that you are writing things in context and in complete sentences. And you'll see what that looks like here shortly. So here we have that example that we saw last week with the gas mileages of the different vehicles. And you can see the dot plot down here. Again, this one doesn't start at 0 because the smallest value in the data set here is that 14, and then the largest value is that 33. So that's what you're going to range the x-axis of the dot plot. So before we go ahead and describe shape, center, and spread, we're going to go ahead and jump to the next slide where it describes the different measures of shape and, or I guess terms for shape, I should say. And then we'll bounce back to this slide so that we can describe those terms. So when we describe a distribution's shape, we say something is roughly symmetric, and it is important that we use a term like roughly or approximately symmetric if the left and right hand sides are approximately the same or mirror images of one another. If we just say that the distribution is symmetric, then sometimes it's implied that it's perfectly symmetric, which typically is not the case with real world data. So we always want to make sure we throw those LY descriptors in there. So approximately, roughly, fairly symmetric, those things, just to make sure that we're not implying that it's perfectly symmetric. So if we were to draw a smooth curve over a dot plot, for example, of something that is roughly symmetric, then the left and right hand sides would be mirror images of each other. So you might see something that looks kind of like this here, so almost like a bell-shaped curve. Something's considered to be skewed to the right if your right-hand side has more of a stretch than the left. So you'd have a peak over here on the left-hand side and then a further stretch off to the right. And then skewed to the left would be the opposite. So you've got a further stretch on the left-hand side with a peak off to the right if you were to draw a smooth curve over that dot plot. Some other terms that you could use to describe, we have what's called a uniform distribution. And a uniform distribution would be that everything's pretty much the same all the way across. So like you'd have the same number of vehicles at each mile per gallon, for example. So a smooth curve would just really be like rectangular. And then we have what we call the bimodal distribution or a bimodal distribution. And that means that it has two peaks. So here are a few examples of shape. So on the far left-hand side, that dot plot is not perfectly symmetric, but it's roughly symmetric. It's kind of peaked in the center, and then the two tails fall fairly evenly. The middle graph, you have a little bit more of a stretch over here on the left-hand side and a peak over on the right, so that would be skewed to the left. And then over here on the right-hand side, the peak is on the left, and that stretch or longer tail on the right, so that would be skewed to the right. So if I hop back to the cars here, if I were going to describe this distribution, I want to think about the shape, outlier, center, and spread. And so here, one thing that's worth noting is that this car that has 14 miles per gallon and this car that has 18 miles per gallon, they're a little further removed or off to the left than the rest of the data set. So I would say that those are potential outliers. We wouldn't say that they're definitely outliers at this point because, again, we will have a mathematical check for that in the next section, but they don't really seem to fit the general trend. So we would identify those as potential outliers. Otherwise, our data set here is roughly symmetric. You don't really see a longer stretch on one side than the other. So we would say roughly symmetric. You may even argue for bimodal because you do have a couple of categories where it's a little bit more peaked than the other. In terms of the center of the distribution, there are 24 cars here. So that middle value is going to be right around the 12th or 13th vehicle. So we can just count, since these points are now in order, and find where that 12th or 13th vehicle would be. So like right around here in this 28 mile per gallon category. So we would say the median is about 28 miles per gallon. And then we want to talk about the range. So the overall data set spans from 14 to 33 miles per gallon. And when we calculate the range, we actually subtract those two endpoints. So you would take the 33 minus the 14 and get that range of 19 miles per gallon. So we do want to be careful that the range is a singular value that we're calculating and not just giving that span. So in terms of how we would write this out, if it were a AP question, for example, we want to make sure excuse me, that we are talking about things in context. So we would say something like the distribution of gas mileages for 2009 midsize cars is roughly symmetric with two potential outliers, with a median of around 28 miles per gallon and an overall range of 19 miles per gallon. We can also compare distributions. And so when we are comparing distributions, you are still going to discuss the SOCs. So we're still going to go with shape, outliers, center, and spread, but we want to do so in a comparative way. So that means that you're going to use comparative words like more or less, or we can say about the same, or we could say higher or lower, but all of those words are things that we would include. We wouldn't just make a list of SOCs for one group and a list of SOCs for the other and then call it a day when we're asked to compare. So here is another example that you can look at in detail in your book if you're interested in, but it's just distribution of household sizes for South Africa and the UK. So in terms of our descriptors here, we would describe SOCs. So over here in South Africa, if we were to kind of think about a smooth curve, this is probably skewed to the right because you've got a longer stretch on the right-hand side. Whereas down here in the UK, this is a little bit more symmetric, maybe slightly skewed to the left because of this little stretch over here. So I would say either slightly skewed to the left or roughly symmetric, but probably roughly symmetric is better. In terms of any outliers, definitely not any outliers in the UK. There's not anything there that doesn't fit the general trend. In South Africa, I would say that this value here is definitely a potential outlier, and maybe even this one here. So we would say potential outliers, whereas here there's none. And then in terms of finding the center, we can do so in the same way. We can find the median value in both groups, just kind of roughly estimating so that I'm not counting up all of those points. It looks like our median value in South Africa might be somewhere around 7, whereas here maybe around 4. Oops. And then as far as the range goes, you're looking in that overall span. So in South Africa, it looks like maybe the smallest value is about 2 or 3, and this highest value is a little bit above 25. So we'll say that our range for South Africa is going to be maybe about 22. And then down here for the UK, we're going to say that highest value is about 6, maybe that lowest value is 2, so that range is about 4. So in terms of comparing those distributions and making sure that we're doing that using our comparative words that I have over here, we would say something like the distribution of household sizes in South Africa is skewed to the right, where in the UK, the distribution is roughly symmetric. The distribution in South Africa has 2 potential outliers, and we can identify those. We can say at about sizes of about 14 and 25. We then can compare those median values. So median household size in South Africa is much higher at about 7 than it is in the UK at about 4. And then there's much more variability or a larger spread in South Africa than there is in the UK, with a range of about 22 versus 4. We then can also make stem plots when we're looking at quantitative variables. And you guys have made stem plots before. We just want to make sure that we have everything kind of statistically correct when we make a stem and leaf plot. So when you go to make a stem plot, you are going to separate all of your values into a stem and a leaf. And so one thing that we do want to make sure we're careful about is that the leaf is only allowed to be one digit. So just the final digit. Everything else is going to go into the stem. So if you have values that are in the hundreds, your stem is going to be 2 digits. It would be the hundreds and the tens digit. Your leaf would just be the ones digit. And then you're going to put everything into order. So here your stems are going to go from smallest to largest in a vertical column. And then you put a vertical line just to the right. And then the leaves go to the right of the stem, and those also go in order. So your book does separate steps 3 and 4. I would say if you put all your data in order to begin with, you can kind of eliminate this third step and just put those leaves then in order to the right of the stem. One thing that you don't need here is that you don't need commas to separate those leaves, but you do want to watch for even spacing. For the same reason that we use even spacing in a dot plot. You want to make sure that visually you get an impact when you look at the stem and leaf plot in terms of kind of which rows take up the most and least space. And then one thing that tends to be forgotten is that you always need a key that shows what the stem and leaves represent. And you'll see an example here in a minute, and I'll talk about why that's important. So here's an example about how many pairs of shoes that you have, and we're actually going to do something similar to this tomorrow in class. You guys are going to submit your data of how many shoes you have, and we'll use your data set. So in order to make a stem plot here, we do want to look at the data to figure out what our stems and leaves should be. Since everything is in the tens, we can use the tens digit as the stem, and then the ones as the leaf. So here we have data that ranges from, it looks like about 13 is the smallest, up to 57 is the largest. So 10s through 50s means that our stems here are going to be 1 through 5. And then we put our leaves in. Like I said, you can skip this step if you just put everything in an order in advance and then put those leaves in over here in order. So here, this first 3 is really the 13. And then you've got another 13 and another 13, a 15 and a 19, a 22, a 23, and so on. And then you need that key. So here, there's no real reason why they used the 49. You can pick anything. So I could have also said for my key that 1 line 3 equals 13 pairs of shoes. But you do want to show that the vertical line is making the distinction between the tens and the ones digit, because it doesn't always have to be, which we'll see in just a minute. You can also split stems in a stem and leaf plot, and you do that when the data values are kind of bunched up or maybe in a very small range. And so when you split stems, you'll see in just a second what that looks like, but essentially you're going to have a stem, like if you had the tens, like we just saw, you'd have 2 ones for stems and then 2 twos for the 20s and so on. And then you can compare with back-to-back stem plots, which you'll also see momentarily. So here we've got females and males. The female data is the same as it was on the previous slide. And then here's the pairs of shoes for males. So if we want to look at the males and split stems, and maybe this is useful because a lot of the males have less than 10 pairs of shoes. So they're all kind of bunched up together in that category. One thing to make note of is that since we're using the tens digit as the stem, we have things like 7 pairs of shoes. This is 0 for the tens digit and 7 for the ones digit, or the 4 is 0 for the tens and 4 for the ones. So that's why you're seeing zeros over here on the stem plot. So here our male data goes from 4 pairs of shoes up to 38 pairs of shoes. So those stems would have to go from 0 through 3, but we're going to split stems here. So we're going to put in 2 zeros, 2 ones, 2 twos, and 2 threes. These down here are just because we're going to add the females to it in a minute. So if we were only graphing the men, we wouldn't have to worry about it. Then when you make the split stem plot, you put leaves of 0 through 4 on the first line. and then 5 through 9 on the second line. So here you can see that there was only the 1 4 here, and then anybody with 5 to 9 pairs of shoes, anybody between 10 and 14, and then nobody had 15 to 19 pairs of shoes, so that just gets left blank. We don't omit it because if we left that out, then we wouldn't be able to see these gaps here. Like it looks like there's some outliers in the male group with the 35 and 38 pairs of shoes. So you just leave those rows empty for categories that don't have any data values. We can then make it a back-to-back stem plot by putting the females on the other side. And so this is the same as what we saw before. It's just split with these 0 through 4 on the first line, 5 through 9 on the second. You're always counting from the inside out with a stem plot. So when we're looking at the females, they're on the left-hand side. This is still our tens digit and still our ones digit. So this one here with the 3 on the outside is still 13 pairs of shoes. And then you would make a key here as well. And so here with the back-to-back stem plot, again, that allows for comparison. So we would talk about the shapes of the distribution, any potential outliers. And then you can really see over here with the females that they're higher on average than the males. So that comparison is pretty easy to make when you're putting them back-to-back on the same scale or same shared set of stems. So for your assignment tonight, you've got some book work, and then there is an optional Khan Academy if you would like to do that. There is an additional video. I'm having some trouble linking the two together where I want to show you why we might not use the difference between the stem and the leaf as just the difference between the tens and the ones column. So you'll see that video linked for today as well. Okay, so I want to take a look at this legendary worksheet. We are not going to actually make the stem plots here, but just talk about how we can use keys in different ways than just the difference between the tens and ones digit. So here, if you look at this first list of data, we have mostly digits that are in the ones category, we'll say, and then you've got some decimal values following. So here, you wouldn't start with a stem of 0 for everything and then put the ones digit on the right. But what you could do is you could use your ones digit as the stem, and then that line is really going to be the differentiation between the ones digit and then the tenths digit would be on the right hand side. And you're only allowed to have one leaf, so you wouldn't necessarily keep all of these. So like this one here that's 5.185, we would either round, which would mean we would round that to like 5.2, or we would truncate, which just means that you would cut off anything beyond the tenths digit. And there's really not a right or wrong way to go about that, just as long as you mark what you do. So here for list 1, let's see, I would say that I'm going to round to the nearest tenth. And then after I do that, I would do something like this 5.7 here. I would say 5 line 7 is equal to 5.7 for my key. And then something else that we wanted to talk about on this worksheet is just whether or not it would be valuable to split the stems. So just kind of looking at the overall range of this data set and how bunched up things might be. So my data here is really mostly between 4 and 7. So it would be pretty condensed because most of them are in the 5s if I just did one stem per ones digit. So here it might make sense to split the stems. And there's not really a guideline as to when you'd want to split or not. It's just kind of looking at how condensed does that data appear. Okay, so if I come over here to list 2 in the middle, list 2, my data has a pretty wide range. I think the smallest value in this data set is 111. The biggest is 1,000. So if I was going to use the ones as the leaf, then that means that my stem would have to go from 11 all the way up to 100. So I would have this really long vertically stretched stem and leaf plot, which really wouldn't be very informative. So here it would probably also make sense to round or truncate. And if you're unclear what I mean by truncate, that means that we would just cut off that last digit. So it would just be cut off that 1, cut off that 0, cut off that 4. So we wouldn't round anything. So for example, this 636 would just be a 63. We wouldn't round that up to 640 and then cut it off. And there's really, again, not a right way to decide whether to round or truncate. You just decide what you're going to do. So I'm going to go ahead and say here for list 2 that I'm going to truncate the 1s. And then I would go ahead and say that 5 line 3 is really equal to 530. And really, when you would go from the truncated data back to your key, you don't know what that 1's digit is. So you would just put in a 0 there. Or if it was rounded, it would be the same thing. We would say that 5 line 3 is 530. In this case, it probably doesn't make sense to split stems because then you are going, or you do still have a wide range of data. It's not really as bunched up as this list 1. List 3 on the far right, this looks more like some of the examples we had in the notes. So our data here, we're really going from the teens into the 30s. So here we don't really need to round or truncate or anything. We can just say that 2 line 8 is actually equal to 28 for our key. But in this case, that data is kind of bunched up. So it might make sense to split stems here. Because without splitting stems, it looks like our data would just be in the 10s, 20s, and 30s.